Now that I've taught you about alpha diagrams and you're recalling what you learned about titration curves and you've put them into the context of polyprotic acids, it's instructive to take a look at a comparison of the alpha diagrams generated for compounds and the corresponding titration curves to see that there's an awful lot that they share in common. Right off, as we take a look at this first example, the famous example of a phosphoric acid case, you'll notice that because phosphoric acid has well-separated k-values that are about 4 orders of magnitude apart, it makes for these really pretty-looking alpha diagrams. The crossing points in the alpha diagrams at the 50-50 point are all right about the halfway point. The titration curves have equivalence points which are very sharp and distinct from each other. Now, having said all that, we can see that lots and lots of things turn out to be the case here that are equivalent. So, for example, if I want to find out where the pH equals the pK, I can see it here on the alpha diagram, and I can see it here at half the volume on the titration curve. So that information is the same. The dissociation appears to be the same, H3A becoming H2A minus, becoming HA double minus, becoming A triple minus. You see the same thing over here as I go from H3A through the buffer to H2A minus, through to a new buffer, to a new endpoint, and so on. Notice also that I can talk about all the regions that are associated with the different kinds of chemical systems. There's my weak acid region, my buffer region, my amphiprotic region, my buffer region, my amphiprotic region, my buffer region, my weak base region. See similar sorts of things over here. My weak acid region, buffer region, amphiprotic, buffer, amphiprotic, buffer, and then over here it would continue on. That's very nice. It's also, as I said, idealized. You rarely see it in reality. This is what you actually get to see in reality. This is oxalic acid. And as we take a look at oxalic acid, it turns out that we start to have a problem because the K values start to get close together and things tend to smear. So notice right here, as we do a titration of oxalic acid, ideally it would look like this, and so on. But that's not what really is taking place here. Look at this smear. I want to be able to see this nice and sharp. Oh boy, it so wants to go up and do this, and up and do that. But because my K's are really close together, I see this mess here. My ability to resolve out the pK values is difficult. My ability to find the equivalence point, where exactly is that occurring? Is it occurring maybe right about here? It's certainly a lot harder to see than this one over here. This is getting closer to what we see in the real world. Let me show you, in fact, one of the very first compounds that we started with, which was an amino acid. So as we take a look at this amino acid here, we have 3 pKs to deal with. The problem with these pKs here is that it turns out that while the one that's most acidic is really far apart here for the tyrosine, remember the 2 Kb's, or Kas that are in the basic region, are really close together. As a result, when I'm trying to draw the crossing points here, my HA-2 species doesn't last too long before it goes away. You can see this even more prominently over here in the titration curve that I draw. I see my first equivalence point very easily resolved. Notice over here how far away it is for these K values. And so, sure enough, by the time this goes away and this forms, I have gotten myself way clear of the K2 and the K3. But because my K2 and K3 here are about 1 order of magnitude apart at 9 and 10, that means that by the time I get one dissociation to start to occur here, before it's gone completely down, a new dissociation has started to come back up, and guess what? I can't see where the equivalence points are. That's a far cry from this example right here, where they are easily discernible from each other. Here, it all becomes a smear. Now, I'm not expecting you to be able to work this kind of problem here as an acid-base calculation. I do want you to know, though, a couple things. One, I want you to know that you can still draw alpha diagrams for them easily. Those alpha diagrams can still let you know what species are present in relative amounts at any particular pH. I want you to know that if you really did want to, you could develop all of the equations you needed for the unknowns, 6 in the case of my tyrosine. And if I had 6 equations for 6 unknowns, I could solve a matrix inverse and find my answer, and I would actually know what the pHs were even when my Ks were close together. And I also want you to know that even though this right here appears to be very difficult to discern, there are actually mathematical tools built, believe it or not, on what you've learned in calculus. You would be able to actually go in here and see that very modest inflection that's taking place along here. There really is an inflection taking place here, an inflection taking place here, and by taking the derivatives, believe it or not, by taking the derivatives of these functions here, you can actually see that change occur and be able to assign the pH and the pK at the equivalence point. Now, having said that, this isn't something that's easy to do. There's much less certainty in the measurement, but at least at that point, it allows you to gather information from here in addition to the obvious information here.